Hello everyone, welcome back. The last few videos that I've made for chapter 24 ran a little shorter than usual, so we need a fifth video to finish up with the remainder of the materials in the chapter. And what we're going to do in this video is we're going to look at the electric potentials that are produced by spheres and cylinders of all the different compositions. By that I mean we can have conducting materials, we can have insulating materials, and then those materials can be used to construct solid spheres or solid cylinders, or we can produce spherical shells or cylindrical shells. And so for each of these combinations, we looked at the same combinations for electric fields that would be produced by these items. So now we're going to look at how these constructs would produce electric potentials. So we'll start with a uniformly charged solid conductor, and because it's made of a conducting material, we automatically get that uniform charge distribution about the surface, and our sphere will have a radius of r, and we want to know what will be the electric potential out here at some distance of little r. Now we can actually save ourselves a lot of work by using similar tactics and approaches that we've used in some past videos. The first one that I would like to consider is just the center of charge analogy, where if we have uniform charge distribution all about the sphere, then if I were to cut that sphere in half along all different axes, each cut should have the same amount of charge on either side. And then as we make more and more cuts, we start to see that those cuts have an intersection, which is right at the center of the sphere. And this was the basis behind, oops, I meant that to be the eraser. This is the basis behind the argument for center of charge. In other words, we can take all of the charge of this sphere and we can squeeze it down to a single point in space. And from there, we can argue that the potential out at this location of little r, due to the sphere, will be equivalent to that of a point charge that utilizes the full charge of the sphere. The only thing that we need to happen is that we need to be outside of the sphere. But then there's really nothing to stop us from getting closer and closer and closer to that sphere until we get right to the surface of that sphere, and we can still use the center of charge argument to say that we have all of our charge located at the center of the sphere. The sphere is still going to act like a point charge, and so we can also let the r value for where we are measuring our potential to equal the full radius of that sphere. So as long as we're outside of the sphere, as long as we're outside of the charge, then that sphere will act like a point. And so this is true whether it's the electric field that we're trying to measure or if it's the electric potential that we're trying to measure. Either way, the sphere is going to act like a point charge. And so this is really going to save us some time, because if we can use these concepts and these arguments to our advantage, then we don't have to set up a bunch of integrations just to tell us what we should already know. So we've done the solid conductor. Let's try a solid insulator. And for a solid insulator, the only major difference between the two pictures is that I will have to do some additional work to get that charge spread out uniformly over the surface of the sphere. But once I do that, once I have that uniform charge distribution, then as far as the charge placement goes, I have exactly the same picture as what I did with the solid conductor. And we can once again use the center of charge argument to say that all of the charge on the sphere is going to collapse down to a single point at the center. And we're right back to this analogy again. So there's the solid conductor, there's the solid insulator. Let's see what happens when we try a conducting shell. So now for a conducting shell, we have this empty region inside of the sphere, but for a conductor, all the charge is at the surface. So really the charge placement hasn't changed with respect to the diagram. We use our center of charge argument once again, and we get right back to this analogy. So it looks like as long as we're outside of the sphere, it's always going to act like a point charge. The last thing for us to try is the insulating shell. And again, we might have a little bit of work involved to spread that charge out over the surface, but we would once again get back to this picture here. Now, where this analogy is going to change is if we try to go inside any of these spheres. So far we've remained outside the sphere. We've even gone to the surface of these spheres, but now we have to consider what's going to happen if we actually go somewhere inside of the physical confines of these spheres. So let's go back to the conducting solid scenario. So as long as we're outside the sphere, it acts like a particle. It really doesn't matter what material it's made of, or if it's solid or hollow. If we're outside of it and we have uniform charge distribution, that sphere is going to act like a point charge. But now we have to consider actually going inside the sphere. What's going to happen then? All right, so now actually let's zoom in a little bit. So we're considering the solid conductor. Again, because it's a conductor, all of the charge will spread out at the surface of the sphere. But now we're interested in finding the electric potential at a radius of A. And A is some point inside the structure itself. Now, to do this, what we really need to do is we need to go back to the expression that we had for defining the electric potential. And I'm going to zoom out on this just because the writing's getting too thick there. There we go. So this equation we've seen a couple of times. We use this to set up the system and tell us what the electric potential difference would be. And this means that we have to move between 2 points in space. One of those points is going to be that point at radius A. The other point that I want to use is a point where I already know the potential value in the system. And the closest point for that is at the surface of the sphere, because we already know that if we're at the surface of the sphere will act like a point charge. So that is the potential at the surface of the sphere. Well, so let's travel. Let's go from the surface of the sphere to the radius value of A. Now, when we do that, when we travel inside of the sphere, let's think back to what we know about these spheres. Specifically, what is the electric field inside of a uniformly charged solid conducting sphere? This is something that we already have in our notes from chapter 22. Well, the electric field inside of this uniformly charged solid conducting sphere is 0. And that had to do with all of the electric fields from all of the charges converging and canceling out. We could also use Gauss's law to prove that. If we tried to use Gauss's law at a radius of A, then there would be nothing to enclose in terms of charge. And Gauss's law said you had to have some enclosed charge so that you could relate that to the electric flux. Well, there's no charge to be enclosed, which means there is no electric field. And if there's no electric field, well, does that mean that the potential inside of the sphere is 0? No, it does not. All this means, by having 0 electric field inside of the sphere, just means that the electric potential cannot change. Any change in the electric potential must be 0. Well, that change has to be, let's see, a delta statement would technically be a final minus an initial. Okay, well, we started at the surface of the sphere, which had a potential value that's equal to that. So we'll say the initial potential was what we had at the surface of the sphere. But then we have to take the difference of that with the potential at a radial value of A. But Gauss's law says you don't have any field there, so your potential can't change. And that means that the potential at any point inside of the sphere has to equal the potential at the surface of the sphere itself. So kind of interesting. But think of it like the ring of charge. When it came to the ring of charge, there was a 0 electric field value, but there was an actual finite potential value. Well, what's a sphere except a 3-dimensional circle? So we're still going to have potential values from all of these charges adding up at the center of the sphere, but also we're going to have potentials adding up at every point inside the sphere. And Gauss's law says no field inside the sphere means your potential inside the sphere cannot change. And the only way that that's going to be true is if the potential anywhere inside the sphere equals the potential at the surface. And so that's what we have right there. Well, let's take that idea and apply it to a conducting shell. So now we'll turn our conducting sphere into a conducting shell. And I want to know the potential inside of that sphere. I want to know the potential at that radius of A. But in terms of the placement of the charge and the way that Gauss's law works, we end up with the same result yet again. The potential anywhere inside this hollow conducting sphere is going to equal the potential at the surface of the sphere. End of story. Now we try an insulating shell. The only trick here is we need to get the charge spread out in a uniform distribution, but once we do that, we have exactly the same picture. And as far as the distribution of charge goes, trying to measure the electric potential at a radius of A, we're inside the sphere. Gauss's law says there is no field inside the sphere. Thus, your electric potential cannot change, and so we must have the same potential inside the sphere as what we have at the surface of the sphere. So all three of these cases are turning out to use the same expression. Where this is going to change will be for the insulating solid. For this, I'm going to make a larger sphere because we're going to have to take a closer look at what's happening inside of the sphere. And if you remember doing this for the solid insulating sphere in trying to solve for the electric field, in this case, Gauss's law was able to sample some of the charge, and so we were able to produce an electric field expression. And so that means that we can have a changing electric potential as we move from the surface of the sphere to this point inside. But now I need to know just what amount of charge is going to be used. And the problem is that we have charge inside our Gaussian surface. We have charge outside our Gaussian surface. As far as Gauss's law is concerned, the charge outside of our Gaussian container does not contribute to producing electric field, but any charge outside of our Gaussian surface will contribute to electric potential. And so what we need to do now is we need to do a combination of the two systems. And the best way that we could probably do this would be to break this up into two different case scenarios. One case scenario where we have the insulating shell of material, And then we can have another case where we have the material that was inside of our Gaussian container. So this would have been the Gaussian container value, and we've just removed it from the total amount. So here's what we would have to do. We would have to consider that a point right here on the inside of the shell would be the same as a point right here on the outside of that inner portion. And we would need to figure out how much potential the shell is producing plus how much potential the inner sample portion is producing. And then we can add them together and we'll have the total electric potential at that location. Now that does require a little bit of additional work, but this is nothing that we haven't seen before. We know how to deal with an insulating shell. We know how to deal with an insulating solid. This is going to act like a point charge of radius A. The only thing that we would have to figure out is how much enclosed charge is there. Likewise for the shell, the potential anywhere inside the shell would have to equal the potential anywhere at the surface of the shell, and we've just got done doing that. And so we can add these two together and we can get the potential inside of that insulating solid. That brings us to the end of the charged spheres, and I'm trying to think back to some of the problems that we've worked. I really can't think of any problems or situations where we actually had the solid insulator system. So even though we can do the math for this, I wouldn't worry about having to put it all together. The bigger takeaway from this discussion was just how we can use all of the concepts and the information that we already have at hand to figure out what the different scenarios are going to produce for us. And now that we know that, we can take those same ideas and we can apply them to, well, I'm not going to try and erase all of those. We can apply those same ideas of conducting and insulating materials, solid and hollow materials, to something like a cylinder. So now you have a charged cylinder. Radius R, length of L, and we want to know what the electric potential is going to be at some point Z above the central axis of our cylinder. Well, if we remember back to our discussions about electric fields that are going to be produced by cylinders, we said that as long as we were outside the cylinder would act like a line of charge. And we can still go through all of the math here with the electric potential, but what's going to happen is that we're going to come to the same result as what we did before. As long as we're outside of a uniformly charged cylinder, it doesn't matter what it's made of or if it's solid or a shell. As long as we're outside of it, it's going to act like a line. And we already have the electric potential expression for a line. It's back in our notes. We can even, let's see here. So we're looking for an R value, or in this case it's Z. So as long as we're outside the cylinder, it'll act like a line. We can even go right to the surface of the cylinder. It'll still act like a line. But then if we go inside the cylinder, that's where we have to start considering the different combinations of the construct. If we go inside the cylinder, the electric field inside the cylinder is going to determine how the electric potential can change. And Gauss's law says that if you try to sample an area inside that cylinder, but all the charge is at the surface, as is the case with conducting cylinder, insulating shell, there's no charge to be sampled in there, and so you have electric field equal to 0, which means that your potential cannot change, which means that the electric potential anywhere inside the cylinder has to equal the potential at the surface of the cylinder, exactly like what we had for the spheres. So a lot of this can be justified just by going through the concepts and the principles of the physics. Obviously, we can spend a lot more time going through the math to prove this, but at this point, it's really not necessary. One of the best things about physics is that once you prove the mathematics for a certain scenario, and you can apply that to another situation, well, why not just apply that concept? Why not just apply that result? We don't have to constantly derive or reprove these systems again and again. We only have to do it the one time. All right, for the second part of this video, we're going to take that same equation of delta V equals negative E dot ds. And this equation said that we could find the difference in potentials between 2 points in space if we integrated the electric field with respect to our displacement between those 2 points. And that would allow us to find out how the electric potential was changing. So in other words, we started over here and we got this information as a result. Now we want to go the other way. If we know information about the electric potential of a system, or how that electric potential is changing, can we use that information to tell us what the electric field in the system looks like? And with any kind of mathematical system, if you can go one way with the math, you should be able to get back to your original starting point. So all of this information that we have available to us right now, keep in mind that all of this started back with the idea of work being done by a force, and that work was going to be responsible for moving a charge through space. So let's take a moment and just bring the charge back in. I'm going to reincorporate the charge into this system. So over here on this side, QE was force, ds was displacement, force dot displacement is work, and work causes a change in potential energy with that minus sign there, so that, you know, this is something that we had back at the very first video for this chapter. Well, we used that to help us figure out how the electric potential in the system was changing. So now let's see if we can go backwards in the math. So I'm going to take the charge back out, and once the charge is removed, we no longer have energy and work. We have our change in potential, and we have our integral statement. My goal is to find the electric field. To do that, I need to remove it from that integral expression. The only way to really do that is if I perform a derivative to cancel out the integral. Integrals are also called antiderivatives, and so if I apply a derivative to each side of this expression, that should get rid of the integral sign, and it should free up the electric field expression so that I can start moving things around with some algebra. So here's how we're going to do that. I'll take an integral and apply a derivative to it. But what derivative do I want to apply? Well, if you remember from a lot of your integration, let's say you had like x to the third, and you were going to take a derivative with respect to x. Well, that would be 3x squared, right? But we could just as easily move that dx up to the other side. So you remember in a lot of your integral expressions, after you go through and you take the derivative, you have that extra dx on the end. Well, that's where this essentially came from, because the integral says we're adding up the influence of the electric field as we move through space. But as we move through space, the electric potential is changing. So there is a changing rate comparison that can be made. And that is going to be made by essentially dividing each side by ds. And what we have now is kind of a strange setup in terms of the calculus, but I have a changing potential versus a changing value of position or displacement. And down here, this implies that the change is infinitesimal. Up here, the delta implies all of the change. So we're gonna update this to say that we're gonna look at the infinitesimal change of our electric potential with respect to position. And once we do that, we now have a derivative statement over here on the right-hand side, and now I actually know what kind of derivative needs to be taken with respect to the other side with the integral. So our ds integral derivative, all that stuff's going to cancel out. And what we have left here is a fairly straightforward expression for electric field. Now I'm gonna bring the minus sign over to the other side, and that's our expression. That's how we're going to find the electric field in this system. The big problem, however, is that any electric potential expression is a scalar. Electric field has to be a vector. When we went from when we started with this expression, we performed a dot product that brought us over to a scalar representation. Well, now we're expected to take a scalar representation and reproduce vector information, specifically directions associated with those vectors. Well, potential is a scalar. Potential doesn't have any of that vector direction information. So how do we bring that back into the fold? The way we're going to do that is we're going to take this expression that we just made, and we're going to split it up into 3 different axes. One for the x direction, one for the y direction, one for the z direction. The way that we can accomplish this is by taking ds, and if you remember, ds is any path through space that we want to take. So ds, we can travel through some region of space that has electric field lines, but ds can travel in the x direction, it can travel in the y direction, it can travel in the z direction. So ds can have infinitesimal components in every direction of Cartesian space. We're going to basically pare this down into individual axes. Our statement says that we need to look at how the electric potential changes with respect to our displacement. Well, why would we want to do that in 3D if we could do it individually in one dimension at a time? So what we need to do is we need to take this change in electric potential with respect to one axis at a time. We'll look at how the electric potential changes with respect to the x-axis. We'll look at how the electric potential changes with respect to the y-axis and with respect to the z-axis. Now, because we're limiting the direction that we're traveling in any given case, the best that we can get out of each of these expressions is the electric field component along that axis. And that really is exactly what we want. It's always better if we can have components of any vector. And so we can actually find the XYZ components of the electric field, and then if we have to put them back together in in magnitude direction form, no problem, we can do that. But this is not the appropriate representation for these derivatives. What we need to do is we need to rewrite these expressions so that a person knows that we are only taking the derivative with respect to one variable at a time. Case in point, I'm gonna start us with an example here. We're going to have an electric potential function of 3x squared y to the 4th z minus 2x y cubed z squared. I know, looks kind of like a nightmare. But this electric potential is going to change as we travel through Cartesian space. So if I wanted to know what is the electric potential at the point 1, 1, 1, well, everywhere where there's an x, I'll plug in a 1. Everywhere there's a y, I'll plug in a 1. Everywhere there's a z, I'll plug in a 1. And this makes it pretty straightforward. I get 3 minus 2, or 1. volt. And then let's do let's do 1, 2, 3, just for the sake of showing. So X, everywhere where there's an X, I put in a 1. Everywhere where there's a Y, I put in a 2. Z is 3. And then we need to evaluate this. So we have 3, 1, 16, 3, minus 2, 1, 8, 9. So we would have to carry out the multiplication for that, take the difference. And so I need my calculator to do that. Alright, so the first term is going to give us 144. Is that right? Yep, I think so. 144 minus, and we have 8 times 9 times 2 times 1 is, wasn't expecting that to happen. This is also 144. Okay, that was weird, but we now have 0 volts. And if we were to move from one point to another, we could now describe the change in the electric potential for this system. If we started here, this would be our initial potential. If we ended there, that would be our final potential. So the change in potential, final minus initial, 0 minus 1. So there would be a potential change of -1 volt by moving between those two locations in space. But now I want to know, what is the electric field in this region of space? We have this nice function here that tells us how the electric potential is changing. Let's use it to tell us what the electric field in this system looks like. So now is where we need to modify the derivative statements that we have up above. Get rid of this stuff. Right. Well, what do I mean by modifying these derivative statements? We're going to take a derivative of our potential function, but our potential function has 3 different variables in it. We have x, we have y, we have z. Each derivative up above is only accounting for one variable at a time. So I can only take the derivative with respect to x as a variable. And to remind ourselves of that, and everyone else that looks at our work, we are going to use sort of an italicized upside down row. And this is the notation for what is called a partial derivative. Partial meaning we take the derivative of one part of the total function. In this case, we're taking the derivative with respect to x only. Here, we take the derivative with respect to y only. And here we're going to take the derivative with respect to z only. So these are the proper notations. And it tells everyone that looks at it, okay, this is going to be a partial derivative. And now we're going to look at how these partial derivatives work. For those of you that are taking Calc 3, you'll learn the partial derivative approach. For those of you that have not taken Calc 3, not to worry, we're learning it right here, right now. So I'm going to show you how to take this partial derivative. And then when you get to Calc 3, you'll know all about it, and you'll get an A on that assignment. All right, so we want to find the X component of the electric field within this region of electric potential. So we have the partial derivative of V with respect to X. That minus sign there, that's been following us along the whole way since the very beginning of this discussion. So don't just ignore it. It's there. Put it in there right now before you forget it. And now we need to go through and take the derivative of our potential function with respect to X only. So X is the only thing that is allowed to change. That means that all of your other variables need to be locked in place. In other words, we're going to treat the other variables like constants. So you remember how constants are treated in derivatives? That's how we're going to treat y and z. Now we have two different terms, so we can take the derivative of each term individually. The derivative of the first term with respect to x is going to be 6x to the first power. And then yz just come along for the ride, because they're constants. Then we have to subtract the derivative of the next term. And we're going to take the derivative of that with respect to x only. That is going to give us 2x to the 0, or 1, times y cubed z squared. And so that is the X component of our electric field. Now, just like the electric potential function, this is a function as well. So how am I supposed to know what the X component of this electric field is at any given point in space? Well, in that case, plug in some values. Let's say we want to know what is the X component of the electric field at the point 1, 1, 1 in Cartesian space. So now we plug in 1 for X, 1 for Y, 1 for Z, and we would get 6 minus 2 with a minus sign out front. So that would be -4. But I wouldn't worry too much about evaluating just yet. The important part for this discussion is making sure that we're understanding the partial derivative process. Okay, so now we need to find the y component of the electric field. And we're going to do that by taking the partial derivative of our electric potential with respect to y. Excuse me. Once again, there's that minus sign in front of your partial derivative. Don't ignore that. Put that down right away. And then we'll go through and take our partial derivative of each term with respect to y. Excuse me. Just got a tickle in my throat. Derivative of first term with respect to y is going to be 12. Switch back to the color there. I'm going to have 12. X is now going to be treated as a constant because we're taking our derivative with respect to y. We're now going to drop down to y to the third power, z to the first. And then we have 6x y squared z squared. That's our y component of electric field. And the nice thing about these components is that we're getting functions that describe the component at every point in space. All we have to do is plug in what point in space we want to measure these things at. So since we did this one at 111, we'll find this one at 111. And we get 12 minus 6 or negative 6. If you remember the units for electric field, newtons per coulomb. And then we need to do this one more time for the z component of our electric field. Again, don't ignore the minus sign that's out front. Put that in right away. And doesn't want to let me zoom out of the screen right now. But we need one more round of partial derivatives. So we need to take partial derivative of each term. For that first term, we should just get 3x squared y to the fourth because we have a z to the first power. So 3x squared y to the fourth. And then the second term, we have the negative 2xy cubed z squared. So that's going to bring the 2 down. We should end up with a 4xy cubed z. And there was the minus sign out front, so that minus sign will go there. And this is now the function that describes the z component of our electric field. And just like the other two, we'll go ahead and evaluate that at the point 111 out in space. That's going to give us 3 minus 4, which is a positive 1. And now that we have all of that information, we can put these components together. We have e of x is negative 4, e of y is negative 6, e of z is positive 1. So there is the three-dimensional electric field in its component form as measured at the point 111 in Cartesian space. From here we can then answer the question, what is the magnitude of that electric field? For that, we have our magnitude mantra, square root of the sum of the squares. Even though we have a three-dimensional vector, that does not change the mantra. We're still going to square every component, add them together, take the square root. Remember, when you square, you lose the negative signs along the way. And so I'm getting a magnitude of 7.28 newtons per coulomb. And this is, of course, assuming that all of these Cartesian values that I've been plugging in here, we've been looking at the point 111. That would have to be in meters. But our potential function, that would have to be in volts. Again, all the x, y, z values would have to be in meters. But now we can see how we can take a potential function for electric potential, and we can convert it back to the appropriate x, y, z values of the electric field vectors. Now, again, I realize that this is a this is a pretty nightmarish function to be using, but I wanted to put in a number of different XYZs to different powers to show you how the partial derivative process plays out. And now that we've seen that, I think you can agree with me. The partial derivative is a pretty straightforward process. Again, you're just going to take the derivative with respect to that one variable, treat everything else like a constant, bring it along for the ride. One thing that we did not have for an example here, let's say we have a different potential function. We'll do 7xy cubed plus 3yz. So the x component of the electric field, this would be negative, partial with respect to x. That would be 7y cubed plus 0. Why'd the second term go to 0? Well, because the second term did not have any x's in it. And so this whole second term, as far as the partial derivative is concerned, is just a constant. And whenever we take the derivative of a constant, we get 0. E of y, we have negative partial with respect to y. This would be 21xy squared plus 3z. No surprises there. And then e of z, negative partial with respect to z. And that would result in 0 plus 3y. So why'd the first term go to 0? Well, because there were no z's in it. Now, z is the variable that we're integrating with respect to. That means everything else is treated like a constant. Derivative of a constant is 0. So, there we have it. We started with our potential function, and within about 30 seconds, we were able to produce the x, y, and z components of the electric field in function form. Now, I would not try to put all of this into a single vector expression. Don't try to find magnitude or anything like that. Wait until you're actually given a Cartesian set, like 1, -2, 0. Then plug those numbers in and find out what the individual values of each of these components is going to be. All right, I think that will finally bring us to the end of chapter 24. So we're going to take a lot of this information concerning electric potential, and we're going to start applying it to circuits next. So for those of you that have taken circuits in the past, this next couple of chapters should be pretty straightforward. I will comment that the major difference between how we do circuits in physics versus how you do circuits in your circuits class, you're going to focus a lot more on the functionality and the output of the different circuit components in a circuits class. What we are going to do is we are going to start from scratch, building up the foundation and explaining how each of these circuit components is actually working. And then once we know how they work, we can apply the function of those circuit elements to the larger circuit constructs. All right, so that is the end of chapter 24. I'll see you back here for chapter 25.